So I'm just going to walk through a little bit of like how Pca is used. So I kind of mentioned that one thing you can do is build up, what's it called? You can use it to do dimensional reduction by basically getting rid of your weakest component. Basically your component that gives the least amount of information. You can also do this as kind of an interesting idea of combining to get rid of correlations, basically trying to pull out the most independent information from it. So I'll kind of mention about what this looks like. But before I do, like I said, eigenvector, proper characteristic, the true one, right? There's a couple of videos. I think these are from 3 Blue, 1 Brown. I mentioned this before, linear transformations, and he talks about eigenvectors and eigenvalues. He kind of talks about like where this comes from. So if you want to kind of see like more of the mathematics, you can kind of look at this and see how this math is able to figure this out. But in order to do this, you would have to make sure you understand linear transformations, which are basically matrices. And then saying from these matrices, this A right here is a linear transformation, and that can figure out this eigenvector. Note that this lambda here is also part of this eigenvector called the eigenvalue, a special value that allows you to pull out this information. But again, I'm not going to focus completely on that because I don't think it's necessary to do the principal component. Okay. So this is just kind of a quick review of going through like what Pca does. Basically, we're trying to find that axis, and if you did the mathematics to find this eigenvector, which is the principal component, it will center it along the data. So like I mentioned before, is that it will always have it to start off at 0. So you have this like kind of like balance between like, oh, here's the data on the left, here's data on the right. And you'll always have that balance. So kind of try to center the best way. And it is literally finding the best way to represent this, which is pretty cool. But let's see here. Yeah, I'm gonna skip over. So one thing I think the curriculum kind of mentions, like this is like drawing a new coordinate system with the coordinates being of length unity, meaning length of 1. If you imagine back to here, what we're really saying is like, oh, you can draw these new lines, these new axes, and you can say, okay, this axis is going to be a measurements of 1 unit across each part. And so you have essentially a new way to measure your data on these new axes. But I'm not going to focus too strong on that part. So anyway, the part that you should really remember is that the principal axis, the principal component, is the most important one. And then the spread of the value for each axis, basically that spread is telling us how much information you have, how much variance there is on that axis. And the more variance you have, the more information there is. So the more important one. So you have a more important axis or component. It's your principal component. It's your top component. Okay. So that is kind of like the overview of pretty much what I kind of just said from earlier, but I'm just kind of reiterating to kind of emphasize the points. Now, what's really cool about this is we can kind of think of this intuitively of like what this means. So if you remember back to like when we did our, what's it called, our module 1 project, and we had these correlated values. So I think we even had this exact example. And to be frank, this school ranking and neighborhood safety, this kind of example didn't come from me. But anyway, it's very related to what we have. So we had like something like square foot and number of rooms. You can imagine that this together are probably correlated together, right? Like knowing about houses, you know, if you have a larger house, you likely will have more number of rooms, right? So you can think of this kind of combining together into being something like some arbitrary like idea called the size of the house, right? So you can imagine like, oh, if I combine, like if I were to think of the square footage, the number of rooms, you know, something like that, like maybe even like yard, you know, how big your yard is, that would give some concept of the size of the house, right? This component, this, you know, feature doesn't really exist, right? At least in this data set, it doesn't have, it's not there, right? But you can imagine if we increase the square footage, we'd also increase the number of rooms. So that would give us a size part. I'll argue that you can probably combine this right here, like how many crimes, you know, for example, happen in this neighborhood or in the zip code, and then how much your like the school rankings in that zip code too. And you might say something like, you know, oh, like for example, this kind of represents like how good the neighborhood is, right? Mm-hmm. Whatever kind of that means by good. And you can notice that this is kind of like really fuzzy stuff, right? Like how exactly do you measure this together? And actually, I've seen people on the project from like Mod 1 project. Wow, taking a long time to spell the neighborhood. There we go. But you can, I've actually seen people try to make this metric. They try to say, hey, can I combine these together and make like a new feature? It does this. And that's actually what principal component is doing. PCA is trying to figure out the best feature for you, and literally like the best feature, and try to pull this out. Now, in reality, if you give it these like 4 different features with different values, it probably is not going to make principal components that is something called the size or good neighborhood. But analogy-wise, you can imagine how you can combine certain features to kind of make into one super feature, like kind of like a more powerful, more explanatory feature. What's nice too is because principal component analysis can always give you 4 features. Like let's say if you start with 4 features, you have now 4 principal components. You might have something where like, oh, here's the first principal component, P1, and then P2, and P3, and P4, right? So if I were to use P1, P2, P3, P4 for my model, this will contain all the information that was in the original feature set. However, if I want to reduce the complexity of it, right, what could I do?
Drop P4.
Yeah, I could drop P4. I could even drop P3 and just keep it 2-dimensional and basically use this and say, hey, this is where most of the information is holding anyway. And you can actually plot this and say, hey, or not just plot this, but also use this to train your model and say, hey, model, these are the most important features. I don't even want to think about that extra stuff because that's probably just noise anyway. Like that's not really giving us that much information. So just look at the main part of these principal components. And that's why if you look at, for example, in sklearns, if you use like PCA, there's an option called N components. So anyone who's done like the lab for section 37, you'll see probably something like to use N components. You can do it one of 2 ways. One is you can say how many features there are. So for example, or how many features you want. You say, I only want the top 2 features. Or you can say, I only want a certain percentage. So I only want 50% of the features. So you can declare it either way of this way. This way, PCA, at least in sklearns package, you can say, oh, I just want either just 2 features or 3 features or whatever. Or you can say, hey, I want only half of the features. So give me the most important half or the most important 75% of the principal components. And this can reduce your dimensionality, reduce your complexity. It can actually help improve your model because basically you're getting rid of that extra noise that it doesn't really need to know.
Is it only the number of features you can select, or can you say, I want like 60% of the information, however many features that is?
Oh, I get what you're saying. You know what? I wonder if, I actually don't know off the top of my head if you can do something like that. Let's see here. Let's check it out real quick. So this is the number of components I was mentioning about. You might be able to do something like that. I guess not. So one thing that's kind of nice is because this will be deterministic in the sense that your components, remember, there's only the best component, right? What you could do is just say, hey, give me all the components, which is the default, is basically just passing nothing, and say, okay, let me go ahead and start off and see how much variation is from each of those parts. So you could probably automate that part, but it doesn't look like sklearn actually will pass and say, oh, give me this percentage, whatever that really means of information. Good question though. So anyway, that's kind of like how you would use, how this works, or how you would use it, or why you would use this for doing modeling, or reducing the dimension and everything like that. Does that make sense so far for everyone?
Yeah.
Like,
another question. So we had,
yeah,
in the example you're talking about, we have 4 features. And if we decide to go with 2 components, then that's going to be taking information from all 4 of those features, correct? We just don't know how exactly.
That's right. So it's not going to be intuitive. And in fact, in reality, it's probably not going to combine square foot and rooms. It's probably going to combine all 4 in some way that it finds, quote unquote, it finds the best way. And this is why we call it unsupervised, because we're not telling it what to do. We're just saying, do whatever you find is best. And based on the algorithm, it's finding what's best. Note that we're not guiding it into how to find those parts.
Right. So there could be some kind of magical mathematical formula that linked square footage and neighborhood safety.
At least for that data set, exactly.
Yeah, yeah.
Yeah, and that's a good way to think of it, is that it's doing whatever is mathematically optimal for that data set, which means you have no control over it, but it means it's also powerful because it means that you will get literally the best one. Now, note that means if your data is not good, it's a little biased or whatnot, then it's not going to perform very well, right? It's like, because it's going to notice those biases, it's going to say, oh, these are the most important ones, but maybe your data set didn't include some other things that were, maybe it's like has a couple outliers, but in reality, those outliers are much more common. Then it's not going to include that information, say, oh, this isn't a really important feature, when in fact it might be. So at least in the overall population.
Do you get a danger of overfitting to your specific data set then too?
I wouldn't call it overfitting necessarily.
Okay.
I would call it more in the sense of like bias, that your data set might not, I guess you can think bias in a sense being overfitting to from the population. So like you're using your sample that's not actually like a good sample of the real population. Essentially what you have to do, that's all you had to work with. Well, then you're not going to do very well when you generalize. So I guess in a way you can say you're overfitting, but I would call it more bias.
Yes. Okay. So based on the data set being biased.
That's right. Yeah. You want basically good data. So yeah, cool. All right. So because again, kind of reiterating when you would use this, right? One is basically what we call these like latent features. So these latent features are basically like, I like to call them like super features. They're features that are combined from the original features to make something else, basically something that didn't exist before. So like mentioning about like the square footage and number of rooms combining together to be like, oh, this is the size feature. Again, I want to emphasize that, you know, if we are using this like in the human sense, the algorithm PCA doesn't know any better about like, you know, what thing to pick. It just knows this is the best thing to pick based on the data. And then of course we can do dimensionality reduction by taking something, okay, give me the most important features and then dropping the other ones. There's a few reasons why you will do, like might want to do this. One is that you can visualize higher dimensions. So if you have something that's a 10-dimensional set, but most of your features are fit within 2 or 3, you know, principal components. You can then plot those principal components and get most of the information of what this 10-dimensional set is looking like. What is nice is that the curse of dimensionality is that if you have many features, you tend to have things to be very far apart, so it can really optimize in plotting these parts in here. But basically, it means that you can plot out higher dimensions a little bit easier. Note though, when you do dimensional reduction, you are losing some information, which might actually be a real reason why. You might want to do this to reduce noise. So you can actually drop those least important components and get rid of most of that extra noise that really didn't affect, like didn't really help, you know, in learning. It doesn't really, maybe just random noise and stuff like that for other reasons. You can do that to help reduce that. And also you can do things like pre-processing. So this is actually really great for like, you know, doing for other machine learning algorithms. So it's very, very common, for example, to do PCA. So you might do something like you just standardize your features or your values. So you do like a standard scalar transformation, transform it into basically some value between 0 and 1 or -1 and 1. Use PCA to basically find the best feature, like basically the best features, and then train on those features. And that can actually help you say, okay, like you're getting rid of this noise, but also it can help you actually perform a lot better, because essentially it has, if it makes an adjustment in one of those principal components, it's going to have like the most amount of information to like really play with, versus if it had to play with X1 and X2 at the same time in order to get that same boost, it's not going to find that as easily. So you tend to have a lot more better performance when you actually use PCA first. So PCA is very, very commonly used as like a pre-processing step. Okay, cool. Yeah, so that's kind of like overall like PCA. Again, the curriculum kind of mentions it more as like unsupervised learning. It is an unsupervised learning algorithm, but it's more commonly thought more as like a dimensionality reduction tool to basically get rid of correlation, to basically improve your model. Okay. Cool. Any questions? I know we're kind of at time, but were there any questions that were kind of lingering that we didn't cover?
Kind of a random question. Can you, like, going back to this housing example, so no, square footage is like the most important.
Mhm.
Could we keep that and do a PCA on the remaining components, remaining?
I could see someone maybe trying to do that. Yeah, you could technically say, all right, let me just use all of these features and do PCA. To be quite honest, though, I haven't seen that in practice.
Mhm.
And I think that kind of makes sense because when you, by the fact that you are saying square footage is the most important, you also are kind of putting in a bias of saying, like automatically trying to say, hey, square footage is really important, even if the data doesn't say it. But in that case, that might make more sense in the sense you need better data. And that's kind of like the more common approach to it. Because
Okay.
then if you need to say, hey, PCA is not going to find this because you don't have a good examples of this, then even if you were to keep that afterwards, it's still not going to train very well on that square footage feature. So it might make more sense to actually get more data.
Mhm.
Yeah, but that's a good point. I think that's a kind of an interesting approach that you might think to work, but it turns out that might just be better to get more data.